Good morning, everyone. Let's start. Today we're releasing Project 2, and Tenzin is here to introduce it.
Hi. So Project 2 is going to be about transport. So you're going to implement the core parts of a TCP socket using a network simulator developed by Murphy. This network simulator is going to be different from the Project 1. So this is like a POX simulator, POX, that's the name. That'll help you test and validate and interact with your socket implementation. This project is split into 9 stages, similar to how we had 10 stages in the last project. And it's going to be due on November 11th at midnight. Come to office hours if you need any help. Project office hours, not the content ones. Cool.
Can I ask folks to move down? Just makes for a slightly more compact lecture. While we're doing that, quick announcement, the following 4 lectures, we're going to go back to the pattern we tried earlier. We're going to release 4 lectures. These are, again, recordings by Murphy from 2020. The topics they're covering are the DNS, HTTP, Ethernet, and various discovery bootstrap protocols like DHCP and ARP, so that you can start to reason kind of end-to-end from the time you set up your laptop to you download a page. All the steps along the way that are involved. These are, again, Murphy's a fantastic lecturer, as all of you know. I think the feedback we got from the survey was that the recordings were welcome. Everyone enjoyed them. There were some mixed feelings about having a flipped lecture every other lecture because that was adding to time. So we're going to do 1 flipped lecture at the end of the 4 sessions. We're probably going to do a slightly more hands-on walkthrough of the protocols and the setup, DHCP, ARP, DNS, and so on, that we would have covered in these 4 lectures. So just to repeat, no in-person lectures starting this coming Thursday and the following week. Do watch the recordings. We will have quizzes as usual. The following Tuesday, we'll have a flip lecture, and do watch the recording before coming to lecture. Okay, the flip lecture will assume you've watched it. All of this, reminders and details on this will be posted on it. Any questions or thoughts on this before? On the logistics side. Okay, great. So today then is our last lecture on the topic of congestion control. So this is lecture 3 now on congestion control. The last time what we did was really, the recording you watched, I hope, is the gory details of how TCP congestion control works. And actually stepping through the rules for how you increment your window, how you slide it forward, when you retransmit, and so on. Today's lecture is going to be quite different. We're kind of going to take a step back at slightly higher level, the topics we cover. We're both going to look at trying to model the performance of TCP, so moving away from these detailed 1 ACK, 2nd ACK, and so on, as well as a little bit of a critique of TCP. What does it do well? What does it not do well? Which motivates some of the changes and evolution we've seen that are being deployed in TCP. And then finally, we're going to talk about router-assisted congestion control. And some of this is in practice, some of it is in more development, research phase. So we'll talk about all of those ideas. Just to get your head in the right place, we're going to cover a pretty broad range of design ideas. Some of them are fairly, they're still in the research phase, so we're not expecting you in this class to fully understand the idea. But what you should know is what problem is that design trying to address, and the high-level idea for how it's trying to go about solving it. But unlike the TCP congestion control we did, we're not expecting you to know the details of how these ideas work. Okay? So with that, the first topic for today is this TCP throughput equation. And the problem it's trying to answer is the following, which is, we've talked about exactly how TCP works, congestion control, sliding windows, and so on. AIMD, increasing, decreasing your window. But if I asked you a question, given a path, what TCP throughput can you expect as an application developer or as a user? Would you be able to answer? Try it. If I tell you, here's your path, there's a certain round trip time, certain properties, let's say loss rate. It's very hard, right? Because we've studied very low-level mechanisms of how TCP works. you'd probably be able to tell me, well, if your window size was 17 and you got 3 duplicate acts, you would cut your window size to so much, and then you would be able to send so many packets in the network at this point in time. But that's not a very satisfying, that's not how we like to reason about performance at a higher level. We want something a little more compact, a little more general as a way of reasoning about performance. And so that is what the TCP throughput equation tries to give us. So it is a simple model. It makes certain simplifying assumptions because, as you can imagine, there is no clean closed form equation for precisely what TCP throughput you could expect. But the question it's going to answer is, if I tell you you have a path between a source and a destination, and I tell you this is roughly what the round trip time of that path is, and P is the loss rate of the path, then the equation is going to tell you what throughput you can expect as an application developer or as a user. So let's start stepping through how that works. So the simple model starts by the assumption that, let's say that we get a loss every time the sender's congestion window reaches this parameter W max. That's the max window size at which you experience loss. And we're further going to assume that loss is detected using the duplicate ACK mechanism. Okay. What this means is we have no timeouts. It means we have one isolated loss. Okay. So again, just another assumption. And so then if you think about how at the sender size your window is going to evolve, right? Step 1, you get 3 duplicate acts, you've detected a loss. The first thing you should do, cut your window size in half. After this, the phase we should enter is AIMD, so additive increase, multiplicative decrease. So 1 round trip time after we detect the loss, we would expect our window size to be W max by 2 plus 1. 2 round trip time, so plus 1 additional round trip time later, we add plus 2. Yet another round trip time, we add plus 3. Until, in our model, we go up to W max. Right? That's the max window size where, again, we're going to experience a loss. That's by the assumptions of our model. And then at that point, again, cut our window size in half, and we repeat. And so really the evolution of our window size is we're going from W max, cutting in half, to W max by 2, increasing by 1 every round trip time until we hit W max again, and then again cut in half. Okay? So we're increasing by 1 for W max over 2 round trip times. Why W max over 2 round trip times? Because we cut in half to W max by 2, and then we go by 1 every round trip time till we hit W max. So that means we've gone through W max by 2 round trip times. And then we repeat over and over. So with this very simple assumption, what this tells us is the average window size in a round trip time, assuming we're always in this steady behavior of going up and down between half and full, the average window size per round trip time is 3/4 W max. Right? And so the throughput, right, the window is just how many of these packets you've sent. So the throughput is 3/4 W max multiplied by MSS, that's just how many bytes you send in one packet, divided by the round trip time. Because we're sending on average 3/4 of the window in one round trip time. So bytes divided by time, we're getting the throughput. Are we good up to this point? Any questions? Right. So this is already giving us W max expressed in terms of the round trip time. But not W max, throughput expressed in terms of the round trip time. But we still have this term W max over there that's not really a path property. So the next step is to replace W max by something that's an expression of the loss rate. Okay. Any questions up to this point? Okay, so that's going to be our step 2 of the model. So this is now what I'm showing you is the size of the congestion window in terms of number of packets on the y-axis with time on the x-axis. Okay, and so we started with this slow start phase. We reached W max, 1 loss, cut by half, and then we keep going up and down, doing AIMD between those 2 points. We're going to focus, we said we're assuming we stay in this AIMD phase forever, so we're ignoring the initial slow start. And so let's focus now on one of these periods here that I've highlighted in blue with A. And so if we think about our loss rate now in this picture, we've dropped exactly 1 packet, right, for every one of the A packets, the packets that we've sent in that shaded region. So on average, we're losing 1 packet for that entire shaded region. And so our loss rate is 1 over A, where A is the total number of packets that was sent in that shaded region. Yeah? So packet drop rate, P is 1 over A. All that's left to do is calculate how many packets are actually in that shaded region A. And we just said that this period of time is W max over 2 round trip times. Right? Does that make sense to everyone? That's because in every round trip time we're increasing by 1. And we went from W max by 2 to W max. So we had W max by 2 round trip times. Yeah. And we also said that on average, we have 3/4 of W max packets per round trip time. Yeah? So the total number of packets in that shaded region is just the product of those two. And so it's taking 3/4 W max multiplied by half W max, 3/8 W max square. Okay, that's our loss rate in terms of the number of packets. So if I now just replace, move the terms around, I get W max in terms of the loss rate. I plug that into the formula we had earlier for the throughput in terms of W max. And what that gives us now is this function here that is throughput in terms of the round trip time of the path and the loss rate. Let me pause for any questions, or would anyone like me to repeat any aspect of this? Yeah? Maximum segment size. That's the number of bytes that are in a packet. So all the accounting until we put in MSS is in terms of packets per time. So when we multiply by MSS, we're getting to bits per second. Any other questions or any point in this that anyone would like me to repeat? We're going to be using this equation a bit in the slides that follow, so it's good to get it right. Right, yeah. Because we're increasing linearly between half and 1, so the average is 3/4. Yeah? Okay. So given a path, what TCP throughput can we expect? We now know that that throughput is going to be proportional to 1 over RTT, or inversely proportional to the round trip time, and inversely proportional to the square root of the loss rate along that path. You can look through the derivation offline. There's nothing complicated really there. But think about it in terms of intuition. This should make complete sense. Right? Why is it inversely proportional to the round trip time? Because remember, everything we did in TCP, we said you're clocked by ACKs. You wait for the round trip time for an ACK to come back, and then you react. Right? So if my round trip time is smaller, I'm getting ACKs back faster. And so I'm reacting faster. I'm increasing faster. So it makes sense that throughput is inversely proportional. A short round trip time means I'm reacting faster. The same with the loss rate. Right? If I have a high loss on the path, then I'm going to be cutting back more often. So it makes sense that I have lower throughput. If I have very low loss, then I'm going to be increasing and staying there without cutting down. And so again, it makes sense that it's inversely proportional to the loss rate. Okay. So the model makes a number of simplifying assumptions. In particular, we ignored slow start, which is typically fine if you have a long-lived connection where you slow start once and then you're mostly doing AIMD. So that's a fine assumption. It does assume a fixed round trip time. It does assume that we have this very clean loss pattern where I drop exactly 1 packet every time I hit W max. But all of those assumptions aside, this is actually useful because it allows us to kind of take a step back and get away from thinking about individual acts and thinking about the overall behavior of TCP. Okay. So as we'll see in a few slides coming up, you can actually look at this. Just looking at this equation gives you a number of insights on what TCP both does well, but also doesn't do so well, and we'll get to that in a minute. So just to take stock, we've kind of wrapped up TCP congestion control, and we're going to be moving into what does TCP not do well. So let's remind ourselves of the main features of how TCP is doing congestion control. So one, it's host-based with no support from routers. In fact, it's sender-based. All of the intelligence is at the sender. It's loss-based. That's what we're using as our indicator of congestion. We're adapting the time scale at which we adapt is the round-trip time. We start out in slow start. We said we start small with a C wind of 1 and we double it every round-trip time until you have loss. And then in steady state, this kind of the way we adapt to find the correct rate is we do this additive increase, multiplicative decrease. It's a very gentle increase, very conservative drop when you experience loss. And finally, we said that the throughput depends on the round-trip time and the loss rate according to the equation we just derived. So if you look at this now and I ask you to shift your hat a little bit and be a little critical, any thoughts on what in this setup or in this design, the set of design choices, do we not like, or could be problematic, or could be idiosyncratic, or something to comment on? Thoughts? Yep. So we change the rate throughout the process. We're constantly either increasing, decreasing. We're never at a steady state. Great point. Yes, that's one. There are many. So others? Yeah. The fact that it's loss-based. Simo, there are many things about loss-based that can be.
Well, I mean, it's not a direct indicator of congestion.
Right. So loss could be not due to congestion. Absolutely. Anything else about this setup? Anything about senders? Yeah.
We don't really take into account anything about routers. It's purely host-based.
It's purely host-based, which is both a blessing and a curse. We'll get to that. Anything else? Okay, let's look at some of them. I think I have about 8 of them. But so implication number 1 actually comes directly from looking at the TCP throughput equation. We've said that flows get throughput that is inversely proportional to the round-trip time. This is kind of by design, right? We've decided to wait for acknowledgements to come back and decide how to adapt our congestion window based on that. But this has certain implications. So if I showed you a very simple example like this, and I said A1 is talking to B1 over a round-trip time of 100 milliseconds, and A2 to B2 over a round-trip time of 200 milliseconds. What would the TCP throughput equation tell us? What would you expect in terms of the throughput A1 is getting versus A2? A1 has twice the throughput, right? All else being equal, A1 is getting twice the throughput of A2. Right? So TCP is actually unfair in the face of heterogeneous round-trip times. We talked about AIMD and how it converges to efficiency and fairness. If you go back to that example, you'll realize we were assuming they have the same round-trip time. They're reacting at the same time. And so we converged on perfect fairness. But in practice, if you have a short round-trip time, you are ramping up faster, and so you're being greedier in getting your share of the bandwidth. So TCP is not perfectly fair, yeah. Right. So, for example, if sitting in Berkeley, if you're downloading a file from a server in San Francisco, and assuming round-trip time is proportional to geo distance, you will have higher throughput than if you were downloading it from the East Coast, for example, because your round-trip time is smaller. And in fact, when we talk about the web and HTTP, you'll hear Murphy talk about content distribution networks. These are companies like Akamai or Cloudflare that actually cache content very close to users. And it's for a few different reasons. One is just your propagation delay is lower, but you get this additional boost because TCP ramps up faster and gives you better throughput. And so in practice, that's why there's so much of a push. Amongst other reasons, there is a push towards moving content, edge computing and moving content and computation close to users. Any questions on this? So this is one of the, you can call it a problem or not a problem, but there's no solution to it per se. This is just how This is actually TCP as we experience it as internet users. Second implication that comes out of looking at the TCP throughput equation is this question of high-speed TCP. And here the setup is as follows. Let's say you had a path on the internet where your bottleneck capacity, or the capacity at which, as a sender, you could send was 100 gigabits per second. And your round-trip time, let's say, is 100 milliseconds, and you have your usual MSS, 1500 bytes, let's say. If I plug these values into the TCP throughput equation, what this would tell me is that the loss rate I need in order to achieve a throughput of 100 gigabits per second is 2 into 10 to the minus 12, which is just a ridiculously low loss rate. This is saying you have to drop 1 in like 50 billion packets. Or if you do the calculation of how many round-trip times it would take you to ramp up to that rate, you'd be within hours. And so what's going on here? I'm saying that the setup I want is that one flow get 100 gigabits per second. And it has to be able to ramp up. If you put in the numbers here and compute how many packets are in a congestion window for this kind of bandwidth delay product, it's in the thousands, tens of thousands. So I forget what the exact number is, but 80 or 100,000 packets. And so if you think about it, what happens is, let's say I had a congestion window of 100,000 packets, and I lose one packet. TCP is going to cut its congestion window by half down to 50,000 packets. And now it's going to add one packet every 100 milliseconds. But you have 50,000, or order 50,000 packets to ramp back up to. So it's going to take you 50,000 round-trip times to get back up to that high rate. 50,000 round-trip times, multiplied by 100 milliseconds, you'll see that you're spending hours trying to ramp back up to 100 gigabits per second. Okay. So basically, these numbers are not practical, and even a loss rate of 10 to the minus 12, that's approaching the bit error rate of most communication media. So you're pretty much going to guaranteed to encounter loss while you're trying to ramp up to that rate. And so the fundamental problem here that TCP is facing is that in order to scale a single flow to a very high throughput or very high speed link, it's very slow if you're going to do this additive increase where I'm adding one packet every round trip time. And so the usual questions somebody will ask me at this point, anyone have any questions? Okay. The usual question somebody will ask is, how common is this? Like, how often do we have one flow that needs to occupy a 100 gigabit per second path? The answer is it's not very common. So this is not a problem that everyone on the internet faces. Even though we have 100 gig or 10 terabit per second links, they're shared by millions of users. But the scenario, for example, where this comes up, in fact, the teams that brought up this issue, and this is being addressed in the standards bodies, was actually the ESNet. ESNet is the Energy Sciences Network. This is a network built that connects the national labs in the US and connects them also to the Department of Energy. So these are physicists and astrophysicists. They have particle simulators, and they have huge data sets collected from outer space and so on that they need to transfer. And so it is quite common that they really have these very large transfers that they need to move data between sites. And they have built a network that is just for them, not just for them. It goes over the internet, but they've provisioned 100 gigabit per second links between all these labs, and they would like to be able to use them. So it's a really bad situation in which you've deployed this high-speed network, and you effectively can't use it because TCP is getting in the way of achieving that kind of high throughput. And so the solution they've crafted, or that they've been working on, is, it's one of these. It's been in the process of being standardized for a very long time. It's called high-speed TCP, and it does a very simple change to TCP. What would you do if you were in this scenario? If you were being asked to modify TCP's congestion control to fix this issue? Yep. Add more than one. There's one little, absolutely right. So increase faster than one with one additional condition. Remember, you have to be careful to not stomp on other flows. So very close to what you said, that the sender monitors its congestion window, and once it's passed a certain threshold, then it says, okay, I'm in a high-speed regime where I'm not competing for 100 megabits per second. I'm competing for large amounts of bandwidth. I can start ramping up fast because there's a lot of bandwidth available. And so typically what high-speed TCP will do is it will do additive increase up to a threshold, and then after that it will kind of increase as a function of the congestion window. So it's going super linearly after that point. And even when it decreases, it'll decrease a little more modestly than cut in half. Okay, so you're not expected to know the details of how high-speed TCP works, but the idea is to know what the problem is, that TCP increases too slowly if you're trying to occupy these high-speed links. And the basic idea would be increase faster than linearly. Are there other approaches you could think of to solve this problem without changing TCP? And this happens all the time on the internet. Yep. Send more flows, right? Open multiple simultaneous connections. And the other approach that people have proposed is using router-assisted congestion control, which we'll get to in a bit. What do people think about opening multiple connections? Any downside to that as a solution? Kind of solves the problem. You could open 100 connections, get 100x the bandwidth. There's one little reason why it's painful to do so. Yeah? Right. You're getting at it, which is from the viewpoint of an application developer, the nice thing about TCP was it gave us this nice byte stream abstraction. Right? You just said, I have this data to send, go, send it. Open a connection, send it over the connection, you're done. If you're going to open multiple connections, the application now has to reason about how it's partitioning application data across connections. It has to keep track of, oh, this particular connection got reset, let me open it and resend that data. Or maybe one connection is going slow and the other one's going fast. Maybe you have to repartition data across the connections. So there's a little bit more work to do as an application developer, but it's certainly doable.
So is it analogous to like multi-threading OS?
Yeah, I would probably say it's maybe easier than taking your program to be multi-threaded initially, but yes, that's a good analogy actually. Now, implication 3 is this notion we call rate-based congestion control. And so here, this is exactly what someone alluded to earlier, which is that TCP throughput is choppy. Right? We keep that sawtooth pattern that we talked about where you ramp up, you cut down, you ramp up, you cut down. There are certain applications that this is not the natural way for the application to be behaving. In particular, if you think about audio or video or streaming applications, there's a certain rate at which they're sampling audio or video. And the natural behavior for the application is to pick a rate and just transmit data at that rate. Okay. And so the one solution by which you can support such applications comes directly out of the throughput equation. It's what we call equation-based congestion control. And so this is for, imagine that you're an application developer that doesn't actually want to use TCP because of this choppy behavior. So what you could do is send a few packets, measure the round-trip time, estimate the loss rate, plug those values into the TCP throughput equation, and then that's the rate at which you send. Okay. There's also earlier on in the lecture, somebody asked, what about if you have a UDP application and UDP is not doing any congestion control? Shouldn't we be worried about how UDP is competing with TCP? The right way to build a UDP application would be to do exactly this, which is to say what share of the bandwidth would TCP take? I'm going to take the same share, and then I'm just going to send at that rate. Any questions on this? And so the reason we're doing this, following the equation, is telling us that we're allowing a different way of being TCP friendly without actually following TCP's congestion control behavior. Yep. This would typically, there is a standard, again, the RFC number there that is called equation-based congestion control. It doesn't have to be TCP. So you could take the TCP header and you could do TCP reliability if you want, but have the rate be determined by the equation rather than the sliding window. Or it could also be a UDP-based implementation. So it doesn't have to be TCP. Other limitations of TCP congestion control, one that came up earlier, we've talked about this in the past, TCP will confuse loss due to other reasons as being loss due to congestion. For TCP, any loss means it's congestion, it'll cut its rate. So if you have something like you had corruption along the link or something, TCP is not going to know that. It's still going to behave like it has congestion and it's going to cut its rate. So you get lower performance than was necessary. Okay. This again, not necessarily something we have a solution to. Yet another question, how do you think short flows would fare when we have TCP? So the reason this is particularly relevant is most of the measurements will show that most flows are actually very short. There are few packets. So, for example, this is a data point from, I believe, a Google study a few years ago, that 50% of flows have one packet to send, or less than one packet of data. If you think about why this is the case, you think about a lot of data center applications, for example, it's a key value store lookup. Right? You're saying, give me the value corresponding to this key. That's not a long flow. It's a request-response, very short flow. And like 80% of flows have less than 100 kilobytes to send. So that's roughly less than 10 packets in a connection. So if we have a vast majority of flows that are just a small number of packets, what do you think TCP congestion control is going to do? Or what do you think is the downside to doing it, to how TCP does congestion control? Let's start with what would TCP do? Right. So TCP starts a connection in slow start, right? So imagine if I had 4 packets to send. I'm going to send 1 packet, wait for the ACK, send 2 packets, wait for the ACK, send the 4th packet. So I took 3 round-trip times to send 4 packets. That's a ridiculously low throughput. It's roughly 1 packet per round-trip time as our throughput. And we've just said that something like 80% of or 50% of flows, that is the throughput they're going to see. And so this could be a problem because, one, many flows are just never going to leave slow start. So we've done all this work in TCP to find your fair share and to maintain that fair share and to adapt to it. But in fact, most short flows are just going to be in slow start. They're going to take longer than they should have. And that's just what short flows are going to experience. The other issue that turns up, and this is going into the specifics of how TCP does congestion control, is remember we rely heavily on duplicate ACKs to avoid timeouts. But let's say I have 5 or 6 packets in a flow, and the 4th or the 5th packet got lost. I just don't have enough packets in the pipe to trigger duplicate ACKs. And so it's often the case that a short flow, if you have a loss, you're going to see a timeout. And timeouts are very long compared to typical round-trip times. And so again, you're going to get poor performance if you're a short flow. How would you fix this? So first, how much of a problem is this? You might be thinking, wow, if 50% of flows are 1 packet, why did we do all this work in TCP in the first place? Because when you look at the measurements a different way, 50% of flows are very short, 1 or 2 or 5 packets, but 99 or 90% of bytes on the network are coming from long flows. So we call this elephant and mice, where most of the bytes are in these long flows, even though most flows are these short mice flows. And this elephant versus mice is something we'll come back to when we talk about data centers. But back to this problem. So we have lots of short flows. They never leave slow start. They see poorer performance than we would like. They suffer from timeouts. What's a quick, somewhat hacky fix that you could imagine doing? Yeah, so just start with a larger initial window. So this was actually, Google lobbied the standards bodies a few years ago, something called initial window 10, which says let's start with an initial window of 10. So now if you have fewer than 10 packets to send, you just dump them in the network and you're done. So very pragmatic, quick fix to the problem. It doesn't entirely solve the problem because it doesn't solve the problem of not having enough duplicate ACKs to trigger retransmission, so you still incur timeouts. But otherwise, it solves the problem of slow start round-trip times.
Why would you have like a different protocol to deal with like small flows? Because like it seems like two different problems, like sending small flow versus large flow.
That's a great question. Why would you not have a different protocol for short flows? And in fact, in the data center world, there is a lot of work on being able to just send, if you have a short flow, send it off quickly. In practice, this works well enough, right? What is wrong with just saying, I'm going to give you a congestion window of 10, and then it kind of fixes the problem, and you don't have to go and rewrite the networking stack and your kernel. So from a pragmatic standpoint, this solves the problem. There's no particular reason one should. Okay, yet another problem. TCP fills up queues. This is again related to using loss as an indicator of delay. So if you remember, the way TCP works by design It is deliberately trying to find the maximum rate it can send, and the way it's doing that is by causing loss to happen. And so by design, TCP is going to fill up the queue at the bottleneck link. Okay? And if you remember, we said loss follows delay. That means by the time you experience loss, you have definitely experienced delay because you filled the queue and your packets were sitting in a queue, incurring delay before you even saw loss. And this means that delays are large, and they're large for everyone. So imagine that you had bottleneck link, and you had a number of these short flows. You have 1 or 2 packets to send. And if there were no long flows in the network, they would see 0 queuing delay. They would just be going through. And now you have this large flow that fires up, that's transferring, let's say, this 10 gigabyte file. And so that one long flow is filling up all the queues. It's causing delay not just for itself, but for all the flows in the network, because those short flows are also now stuck behind the long flows, and they're sitting in the queue incurring delay. And a particular, this is how TCP was designed to behave. And so it's not like the designers were unaware that this was the behavior. But what really caused this to be a problem was the fact that a lot of vendors started to add more and more memory on routers. And in particular, the very low-end home routers that we have in our home, they have a ridiculous amount of buffer space. And the idea here was that the home router vendors just didn't want to cause packet drops at the home. So they started putting in large buffers. And so we started seeing these very large delays. And so now this packet delay due to queuing can actually be significant on the internet. This is a problem that's called buffer bloat. And this was particularly problematic for people, for service content or internet services that cared about latency. And the canonical example here of when this really annoyed people was when Google started running YouTube. What they found was that the search response time was going down when the users at home were simultaneously watching YouTube. So if you were watching a YouTube video and someone was doing a search in your home, they would see search delays or search response times that were much worse, because sometimes there was seconds of buffering at the home router users. So this is the problem clear? Yeah.
I'm not understanding why a large amount of memory on the router, which is like the hardware on the router, is causing this problem.
Right. So think about what is the router doing, right? Sending packets out over the link. And TCP by design is going to increase its rate until you cause a drop. So what does that mean? The sender is going to keep, let's say it's YouTube in this case, is going to keep trying to send traffic at a higher rate, which means that at your home router going towards the user, the queue at the home router starts filling up. But TCP is going to continue to increase that rate until it sees a drop, which means that your queue at that router is full. So now when a packet comes in at that router, it's going to sit at the top of the queue and wait for that queue to be drained. But if I had, let's say, 10,000 worth of packets that could sit in the queue, that's a very long time for that packet to be delayed. Right. Yeah. Any other questions? Okay, so this is exactly what was the reason why Google started working on this new congestion control algorithm called BBR. And the idea here, what do you think you would do if you were Google trying to fix this problem? You want low delay. Because if you think about it, what is the benefit to sitting in a buffer at a router? There is no benefit from performance or a throughput perspective. Right? We put buffers in because we said traffic is bursty, we want to absorb temporary bursts. But now if we say we're always running with this queue full, it's not helping me in any way really. What would you do to try and fix this? Yep. You could remove the queue. There's a slight concern with that, which you could remove or shrink the queue. So there is a move for telling router vendors, especially home router vendors, not to put so much buffering on home routers. There is a slight concern then that if you have bursts, you cause drops. Yep. Right, so that's actually a neat idea. Not the what BBR did, but you're absolutely right. And this was an idea called random early detection, which was saying as your queue starts filling up, let's proactively toss a packet to tell the sender to slow down. Cute idea, not the one. Let me rephrase the question. What would you do without changing routers? which if you're YouTube or Google, that's the only option you have. Yeah.
What if people don't have first deployments? Don't have
It's an interesting thought. What if you don't have bursty flows? But would that fix the problem? Because the problem here is that TCP is deliberately trying to increase its rate. That's its only way it knows how to stop is to first fill the queue. Yeah. Yeah. So the idea here is what we call delay-based congestion control. This is a very simplified version of what TCP does. So here's what you should understand is what is not TCP, BBR, of what BBR is trying to do. What I would like you to understand is the idea of what BBR is trying to do. And so what BBR is trying to do is to say we still want to run at the maximum throughput possible, the bottleneck or the available capacity of the link. But we want to do that without building up the queue. And so what BBR's insight is to say that as the queue builds up, the signal that I get as a sender manifests in delay. Right? So if I was measuring the delay that a packet takes from the time I send it to the time the ACK comes back, if I'm starting to build a queue or packets are starting to sit in the queue, I should be able to see it by measuring the delay in packets. And so their main idea is to say rather than wait for loss, let's measure delay. Let's get a good idea of what the minimum delay of the path is. So if I could measure delay often enough, the lowest measurement I get, the minimum delay, is an indicator of a reasonable approximation to the delay I can expect without queuing. If I start to see my delay go up beyond that, then I can cut my rate. So it's cutting its rate early when it detects an increase in delay, as opposed to loss. But otherwise, the basic idea of TCP of adapting and searching for, going up and going down, searching for the right rate at which to send, that remains in BBR. The main idea is measure the delay and see whether that's going, and react to delay rather than loss. Okay. Any questions? So again, I don't expect you to know the details of how BBR works, but understand the problem it's solving, which is that TCP builds up queues, and understand the core kind of nugget behind it, which is we're going to measure delay and react to increases in delay. Okay. Cheating with TCP, are there different ways to cheat with TCP? Yeah? Right, so why are we measuring the minimum RTT? Right, so the idea is that your question? Yeah. So the idea in BBR is we don't want the queue to build up. And when the queue builds up, delay increases. But I need to know some idea, I need to have a baseline. What am I comparing to? I need to know what a good delay was like. That good delay is going to be the minimum RTT that I've ever seen. And I'm going to guess or hope that that minimum RTT corresponds to when I had no queuing. Any other questions? Cheating, ways in which you can cheat as a TCP sender. Thoughts? There are lots. If all you controlled was the sender side of your TCP connection, what are things you could do to get a higher throughput? So don't cut your rate in half. That's certainly one. The other one, increase by more than one MSS every round trip time. So in fact, if you walk through the kind of efficiency fairness graphs we did last time, and if you said X is going to increase by 2 every round trip time, while Y is going to increase by 1 every round trip time, you'll see that X gets twice the rate of Y. Right? So a very easy way to get more than your fair share. Yet other ways, just open multiple connections. Right? Again, going back here, if A starts 10 connections to B and D starts 1 connection, then A is going to get 10 times the throughput of D. This is probably the easiest way to get more than your fair share. Use a large initial window. Right? Nothing stops you from starting with a window of 100 packets. Basically, nothing in TCP stops you from not following the rules and just sending more than you should. Does that make sense to people? So, natural question everyone usually asks here is, why has the internet not suffered congestion collapse? we started congestion control by talking about how the reason people put in congestion control was because they experienced congestion collapse. We now have this very sophisticated congestion control algorithm, but we also know we live in a world where there are lots of malicious actors on the internet, and we just said you don't have to follow that congestion control algorithm. Why do you think we're doing okay? And at least as far as I know, there has never been a report of congestion collapse on the internet since the 80s. Yep. Right, so certainly if senders, so there isn't a clean answer, by the way, to this question. Certainly if you had a set of sources that were sending way too much traffic, it would be treated as a denial of service attack, and ISPs would probably rate limit it. But the other reason is, even people who cheat on congestion control, they do back off. So if you go back to, the early cause of congestion control, the TCP implementations at the time, they had a fixed timeout, so they never adapted their timeout, and they never cut back on the rate. So every time there was a timeout, and it could be a short value, it would just dump an entire window into the network. Whereas today, you can, even if you open 10 connections, those 10 connections are going to back off when they experience congestion. Or even if you start with a larger initial congestion window, when you have drops, you will do multiplicative decrease. So while in principle you could just blast packets into the network, that's usually an attack, and that gets rate limited. If you're actually trying to just modify TCP a little bit to get an unfair advantage, that's going to give you an unfair advantage, but it's not going to cause congestion collapse. So that's speculation about why we haven't yet suffered a congestion collapse. The second question then you should ask is, okay, so we don't have congestion collapse, but is fairness or unfairness common on the internet? The answer to that is we actually don't know. There are anecdotal reports that turn up in the press once in a while. So, for example, a few years ago, there was a study that people did showing that BBR actually is not fair. That if you are in certain scenarios where BBR is competing with some other legacy TCP connection, BBR is going to take more than its share of the bandwidth. And so this caused some news reports, and then Google worked with these researchers to fix BBR and so on. But this does happen. What I would not be able to tell you is how common it is. Across the internet, what is the degree of unfairness? And you can imagine this is actually a hard question to answer. In the case of Google and BBR, they open source the system, so people could grab it, experiment with it. But we don't really know what Netflix does. I'm picking on Netflix for no particular reason, but many of these content providers that have closed source implementations, we just wouldn't know. Question? BBR is actually, so if you're talking to a YouTube server, the server, when it's sending you packets, is running BBR. BBR is TCP. It's just a different algorithm for congestion control within TCP. So this is the trick, that congestion control is just an algorithm running at the sender. So it's still TCP. That's a great point. Okay. Yeah.
So who is implementing BBR?
Sorry? The Google is. So, the original implementation for BBR was an addition, a modification to the congestion control algorithms in Linux, for example, and then it's open sourced. So at this point, you could go grab the source code and run BBR on your laptop.
Oh, so this is like on a host?
Yeah. Last point, this is less to do, moving on from cheating and so on. This is partly more of a software engineering kind of practice, is that congestion control is deeply intertwined with reliability. And we talked about this, at length, that if you look at how congestion control is implemented in TCP, the mechanisms are deeply related to how TCP was doing reliability. So we use duplicate acknowledgements, we use acknowledgements, timeouts, we have this notion of window, we have rules around fast retransmit and fast recovery that are all tied to how TCP is doing reliability. And when I first introduced it, I kind of talked about this as being an attractive aspect to how TCP does congestion control. It was a few lines of code change in the TCP implementations at the time. That is a true positive. The downside is it complicates evolution. Right? So when you think about how of modularity in your implementation, we like to have a certain separation of concerns. So for example, if I wanted to move from cumulative acknowledgements to selective acknowledgements, that should be a problem for how we did reliability. But in TCP, it also affects how we do congestion control. We then have to go back and revisit all our fast recovery, fast retransmit rules around congestion control. So this is not necessarily a performance issue, it's more a maintainability of the code issue and a modularity of the software issue. Why, this is relevant is sometimes we want congestion control but not reliability, right? If you have real-time audio or video. But there's no easy way in TCP to turn off the reliability and get the congestion control. You get both. The inverse is also true. I have had struggled to come up with an example application, but sometimes in principle, we could want reliability and not congestion control. Right? Let's say we had that simple request response, so one key value lookup. I don't really need congestion control, but I do want reliability. Again, there's no easy way to turn off congestion control and keep reliability in TCP. So just from a software modularity standpoint, this may not have been the best decision. So quick recap, TCP problems, misled by non-congestive losses, fills up queues, which leads to high delays. Short flows don't really benefit from much of congestion control. AIMD impractical for high-speed links. The sawtooth pattern is choppy, which is not ideal for certain applications. Unfair under heterogeneous RTTs, we don't really have any solution for that. Tightly coupled with how we do reliability, and finally end hosts can cheat. That might seem like a long list. You might feel like, wow, that's a major list of issues with TCP. I actually think with the exception of the possibility that end hosts can cheat, most of these other issues, they're not showstoppers. Right? We have ways of dealing with them or workarounds that are reasonable, which is probably why TCP has persisted so long. What do people think? Is this reasonable? Mostly? The one other observation, though, to make here is that, in fact, and this brings us to the last part of what we were going to cover, is that most of these issues, you could very cleanly fix them if we had some help from routers. Right? And several of you have brought this point up throughout. For example, we are misled by loss, or you have to wait to fill up queues to get loss. Well, routers know the level of congestion they're experiencing. They could just tell end hosts if they're congested. Likewise, if we're unsure of exactly, the sender is unsure of what rate it should send at, maybe the router could just tell you what rate it can accommodate. The routers could send feedback directly back to the senders. And finally, if end hosts can cheat, one strategy is to have routers enforce isolation between flows to make sure that cheating is not an option. And that's kind of at a high level, 3 ways in which what we call router-assisted congestion control. There are many, this is again a large design space, but 3 ways in which it seems most helpful. One is to enforce fairness, so we don't rely on senders doing the right thing. The second is to have a more precise rate adaptation, so senders are not constantly searching for the right rate. And the last is just to have a very direct, explicit way of detecting congestion. So we're going to start with the first one, asking how can routers ensure that each flow gets what we call its fair share. And I've been kind of appealing to your sense of intuition of what fairness meant. We're actually going to define fairness more rigorously at last. Okay, so the basic idea here, what's the setup behind fairness? And you should kind of understand this before we move forward. The setup is, think of it from the viewpoint of a single router. And you're getting a lot of traffic coming in at that router. Those packets belong to certain flows. Right, for certain TCP connections. And as a router, you want to make sure that whatever capacity you have on the link, you're going to share it fairly across those connections or those flows. That's kind of the setup of what we're trying to do. And so consider from everything, next few slides, we're in the viewpoint of a single router and what that router is trying to do. And the way in which the general setup is that a router receives these incoming packets. The first thing the router has to do is know what flow it belongs to, or what TCP connection. So if you remember way back in the earlier lectures, we said there's this 5 tuple that identifies a flow, right? The source address, source IP, destination IP, source port, destination port, protocol field. So think of it as packet comes in, I look at those 5 fields and I decide what flow or connection this packet belongs to. Each flow is then going to have its own queue at the router. It's going to be a FIFO queue, first in, first out. Right? So now we're changing the setup. In the past, we've talked about routers as I pick up a packet, do a lookup, send it on. Now we're saying this kind of router, if it's going to do fairness, it's going to have a queue, a separate queue for every flow. When a packet comes in, it's going to say, you belong to flow 59, and it's going to put that packet into 59's queue. Okay? So now the router has a queue for every flow. And then its main problem is it's going to decide which queue it's going to service, meaning it's first going to pick a queue. It's going to say which flow needs to have its packet sent in order for me to be fair. So it's going to pick a queue and then send the first packet in that queue out. I still haven't told you what fair is and how it's going to decide which queue it should pick, but that's the overall setup. Okay, is that setup clear to everyone? Any questions there? Yep. You could in IPv6, right? And that was exactly what it was. In IPv6, that's the intent of the field is you could look at the flow ID. Fair enough. I'm back in IPv4 land. So now the key question is, what does fair mean exactly? Right? Roughly, intuitively, it means every flow gets kind of the same. But more formally, the form of fairness that we talk about, and again, there are many definitions of fairness, but in networking, the one we typically use is something we call max-min fairness. And the way we define it is as follows. Let's say that the available bandwidth that the router is allocating is C. And let's say that each flow I has a demand R sub I. This is the rate at which the flow would like to send. And so, visually think of it as a pipe there. I get demands R1, R2, R3, so on. I'm trying to compute at the router what allocation of that bandwidth I should give each flow. So the question we have is, what is a fair allocation AI? So AI is the portion of C, the capacity C that's going to be assigned to flow I. Okay? So what allocation AI of the bandwidth should I give to each flow I? And so max-min bandwidth allocations say that each flow I should get an allocation AI that is the minimum of its demand, Ri, and some value I'm going to call F, which is its fair share, where F is a unique value such that, assuming demands exceed the capacity, the sum of AI is equal to C. So let's break that down a little bit. What is this telling me? This tells me that if I'm a flow I either get what I asked for, right? That's Ri, or if I get something less than what I asked for, I get a value F, but I'm guaranteed that no one else in the system got more than F. That's what this equation is telling me. And if the total demand exceeded the capacity, I'm completely using the capacity. That's just for efficiency. Let's do an example, and then we'll come back to the definition, and you can tell me if it's making sense or not. So let's say that C is 10. I have 3 flows, and their demands are 8, 6, and 2. Right. How would I do max-min fair allocations? I would start by saying the fair share, I have 3 flows, I have a capacity of 10, so the fair share is I give every flow, I offer every flow 3.33. So that's my first guess. I take 3.33, but then I see that R3 only needs 2 units. So I'm not going to give it 3.3 when it doesn't need it. So I'm now going to give R3 only 2. Right? And so now I'm left with a capacity of 8. And I've fully met R3's demand. So now I have a capacity of 8 to assign to the remaining 2 flows, R1 and R2. Okay. So if I have 8 units of capacity to assign to 2 flows, that means I could, to be fair, assign each one a value of 4. 4 is less than the demand for either flow 1 or flow 2. Right? So that is the allocation. The value of F is 4. And so the final allocations are going to be 4, 4, and 2. And if you go back to where we said that your allocation has to be the minimum of this fair share or your demand, and you'll see that that holds. Right? Flows 1 and 2 are getting 4, and flow 3 is getting 2 because its demand was less than 4. Yeah. Yep. Because the question is, why is the last one's allocation 2 as opposed to 3.33? Because it's the minimum of your demand and the fair share, F, the value of F that we arrived at, and the value of F was 4. the final value of f. That 3.33 was just an intermediate step in arriving at the final value of f, which is 4.
Is the fair share always the ceiling?
It's, nobody will have more than the fair share in the allocation.
Well,
Yes, in that sense.
Is it the ceiling of the division of C and F? Is it who wrapped up?
No, you mean can it not be a fraction? It can be a fraction if we wanted to. Yeah. I can have 10.4 megabits per second or something. So the key property of maximum fairness is that if you don't get full demand, so if you get something less than your demand, no one gets more than you. And that's why it's fair. Does this make sense to everyone? Yeah. If you think about it, this is what round robin gives you. If we said all packets are the same size, and you basically did round robin, one at a time scheduling, you would get maximum fairness. Does that make sense to everyone? Round robin is a fair scheduler. And so the key question is, how do we deal with packets of different sizes? Because if I have a packet that's 1500 bytes and you have a packet of 40 bytes, it really isn't fair. It could be highly unfair that we both get to send one packet each, one at a time. So this question of different packet sizes actually matters in terms of ensuring fairness. And so the crux of the problem that fair queuing, which we're going to discuss in a minute, tries to address is how do we do maximum fairness, or think of it as how do we do round robin if we have packets of different sizes. That's really the intuition here. And the mental picture you should have is that if I have packets of different sizes, the fair way to treat those packets would be to do round robin on a bit-by-bit basis. I would send one bit from every packet. And of course, this is not practical. We can't do that. We have to send packets. But your mental picture should be, we want to do bit-by-bit round robin. We cannot do this in practice, but we're going to approximate it by using an algorithm we call fair queuing. Okay, so what is the idea behind fair queuing? The idea is that in fair queuing, imagine that the router is going to simulate bit-by-bit round robin. Okay. And I'm not going to tell you exactly how it does this calculation, but the idea here is, given a set of packets, I'm going to simulate if I did bit-by-bit round robin, at what point in time would the last bit in the packet have been transmitted? Okay? And that point in time where the last bit would have been transmitted is what we call the packet's deadline. And then fair queuing is just going to service packets in increasing order of their deadlines. Okay. Does the intuition make sense to everyone? Don't worry about how I do that simulation. But the basic idea is packets are coming in, they're very different lengths. I'm going to pretend I could do bit-by-bit round robin and say, if I could do it, at what time would this packet, the last bit, have been sent? And then I'm going to order the packets based on that time when the last bit could have been sent. And that's the order in which I'm going to send it out. And if I do that, then I'm maximum fair. Okay? So think of it as basically a form of round robin that's extended to the case where not all packets are the same size. Okay. Kind of go bears moment here. This is the paper that introduced fair queuing. It is, Scott Schenker, of course, is on the faculty, though at the time he did the work, he was at Xerox PARC. Srini Keshav was a graduate student at UC Berkeley when he did this work. This is one of the most cited papers in computer science, this idea of fair queuing. The idea of maximum fairness and doing kind of this fluid model, what we call bit-by-bit round robin, had been proposed by actually many years before, decades before that, by someone called Nagel when he introduced the idea of packet switching. But no one knew how to make it practical with different packet sizes, and that's what the fair queuing algorithm gives us. Okay. Here's a quick example. Let's say you had these two flows, and what I'm showing you here is their arrival time. What fair queuing would try to do is to simulate, again, think of this as just a theoretical calculation that's happening, how packets would have been transmitted if I were doing bit-by-bit round robin. And then I would look at the simulation time and say, okay, when was I done sending the packet? And so I would say, okay, first the numbers 1 and 2 from the blue, that's very clean. And then I would say, well, actually now I need to send the first packet from the yellow flow because it was done sending before 3. And then the second packet from the yellow flow and the third packet, so packet number 2 from the yellow flow and 3 from the blue flow, both finish at the same time. And so just to break ties, I'm going to service the packet that arrived first. So I'm going to send blue 3, followed by yellow 2, and so on. Okay. So fair queuing versus FIFO, things to remember. The advantage of fair queuing, if there's one word you should remember, it's isolation. There is a router is going to enforce your fair share. It really doesn't matter as a sender what you were trying to do to cheat. It doesn't work because the router is going to say, here's your fair share, that's as much bandwidth as you get. There's nothing the sender can do to cheat or get more than its fair share. So the share you get doesn't depend on the round trip time. It doesn't depend on any of the details of what rate adjustment scheme the sender used and so on. It's just a simple calculation, local calculation by the router based on the capacity it has. Okay. Disadvantages of fair queuing, we didn't actually go into the details of that algorithm of how you simulate the fluid model or the bit-by-bit round robin. It is far more complex as a bookkeeping mechanism. It's computationally more complex. You also have to, at routers now, have per flow queues or per flow state. You have to do this extra step of classification and determining what the deadlines are. So it is a much more complicated solution. And as we'll see, it's important to remember that fair queuing doesn't solve congestion control. It helps congestion control by providing isolation, and we'll get to that in a minute. So fair queuing in practice, what do you actually see? Pure fair queuing, as I described it and as the original paper described it, is computationally too expensive to implement at high speeds. But over the years, there have been several approximations defined. In particular, one of them is called deficit round robin. We're not going to discuss it, but good to know it exists. And so today, pretty much every router that you can, higher-end router that you can buy, implements deficit round robin. So it implements some form of fair queuing. What it does not do is it does not implement per flow fair queuing. There's, as far as I know, no router that would have enough queues that it could actually do fair queuing for every TCP connection. So instead, there's some number of queues, in the hundreds or so on. And what ISPs will use it for is to provide isolation to certain VIP customers or certain classes of traffic. So there's a certain class of traffic, let's say, particular prefixes, that will have their own queue. And that queue is guaranteed to have its share of the capacity. Okay? Any questions? Right. So fair queuing in the big picture, the point I want you to remember is that fair queuing does not eliminate congestion, it helps us manage congestion. And it's best to see this with an example. So let's say I had this topology here, and I had the green flow and the blue flow. And they're sharing this 1 gigabit per second link in the network. What is fair queuing at that router going to do? It's going to enforce that the blue gets half a gig and green gets half a gig. Any excess is going to be dropped, and there's nothing blue or green can do to get more than half a gig. But that is all that router can do. It's enforcing the fair share for each flow. What this router doesn't know and can't do anything about is the fact that, for example, if I look at the green flow further down its path, its bottleneck link is 100 megabits per second. So that green flow, we're just going to lose, it's going to drop 400 megabits per second, one hop down from this router that gave it half a gig per second. Is this example clear? So this router worked very hard to give the green flow its fair share, and then the flow continued down, and it's getting less than that fair share. So the point here to remember is, we're going to drop an additional 400 megabits per second. The important takeaway is fair queuing is not telling the sender at what rate it should be sending traffic. So we still need all of the kind of congestion detection and the rate adaptation at the sender. Okay? Is this making sense? Yeah?
Is it possible to broadcast these kind of...
Fair shares? Yeah, hold on to that thought, we'll get to it. So the benefit of fair queuing, again, is resilience. Right? You cannot cheat it. It's not subject to all these vagaries and round-trip times and so on. But it's not, you can still get congestion, you can still get packet drops, and senders still need to discover and adapt to their rate. So it's really on that list of problems, that last one about senders cheating, that's the problem that fair queuing is really very effectively solving, I would say. One thing that should be mentioned, per flow fairness, you've probably sat through this discussion thinking, it would be great to have per flow fairness and to have the network enforce it, because of course we would want per flow fairness. You should know, we're not going to go deep into this, that per flow fairness and fairness in general has long been a controversial goal on the internet. And if you think about it, it's, the idea that every flow should get its fair share. at some level is non-intuitive, right? Because what if I have 8 flows and you have 4, right? Why should I get more share than you just because I opened up more connections? That's not quite fair. Right? Or what if my flow is going over 4 hops in the network and your flow is going over 1 hop? In some sense, one might argue that's not fair either because I'm consuming bandwidth at 4 links and you're consuming bandwidth only at 1 link. So maybe you should be getting more at that 1 link than I am getting. Yet another reason ISPs will tell you is I have certain customers that are willing to pay more. That's the kind of fairness I want, not this per flow fairness. Though that particular one, there's something called weighted fair queuing that could help. But nonetheless, these are all reasons why many people will tell you, I don't care about fairness. But what everyone cares about is isolation. The ability to make sure that in the worst case, you're not going to starve a particular flow or starve a particular customer. That is highly useful. What you should know about this, that per flow fairness is not this perfect goal or perfect target to achieve necessarily. Right. So 2 other things I wanted to touch on with related to router-assisted congestion control. One is this, exactly what someone just brought up, this idea of using routers to have more precise rate adaptation. And the idea here is actually exactly what was just brought up. We just discussed how every router could compute the fair share that every flow deserves. Right? You run this fair queuing algorithm and you decide what fair share a particular flow has to have. I then also told you that actually this isn't enough to solve the problem of congestion because flows still don't know what rate they should send at. But one way to fix this is, what if we said a packet carries a rate field and a router inserts a flow's fair share in the packet header. And so think of it as the source sends a packet. That packet is traveling through the network and every router looks at the fair share that that flow is going to get. And if it thinks it has a lower fair share, it overrides it. So as the packet travels through and the ACK comes back, I learn what the minimum rate or my minimum fair share is along the entire path. And then as a sender, you just send at that rate. Does this make intuitive sense to everyone? It's actually a pretty powerful idea if you could do it. Right? And so then the end host just set the sending rate to F. So this is kind of routers really working with senders to achieve congestion control. This is the basic idea behind a proposal called Rate Control Protocol, RCP, that came out of a group from Stanford. And I'd like to show you one result on why RCP was so interesting to people at the time it was proposed. It came out 10 plus years ago, but this finding has inspired many follow-on efforts. So there's a lot going on in this slide, so let me tell you what you should actually look at. On the y-axis here, this graph is showing the flow completion time. So this is the time when all the bytes in the flow were successfully transmitted. And on the x-axis here, it's showing that flow completion time for a particular flow size. Okay, so if you wanted to read a point on this graph, you could say a flow size of 4,000 with TCP, RCP, which is in red, had a flow completion time of, okay, I'm going to make this up, 0.25 or 0.3 or something in terms of time. Okay, so low on this graph is good because it means I'm seeing a shorter flow completion time. And ignore all the black points. That's a protocol called XCP that we're not going to discuss. But what this graph is showing is the flow completion time for TCP in green and comparing it to this proposal we just had for RCP, which is in red. And the only thing to take away here, is what this graph was showing people was if you had something like RCP, you could be doing as much as 10x better than TCP. And this was kind of a shock to many people about how much performance TCP is leaving on the table. And so this is why this idea of router-assisted congestion control, or learning your rate directly from routers, most people today will think it's a very powerful idea. So skipping that slide, where is RCP? It's not something that's actually deployed in practice because very much like fair queuing, it has a certain computational overhead. But this idea, and actually maybe something very RCP-like, is being evaluated in data centers. So this is an idea that many folks in data centers continue to play with. Okay. Last one of the router-assisted congestion control. The idea is, this is a very simple one and widely deployed, is that you could use routers just to detect congestion. And so this is the idea behind a proposal we call ECN, or Explicit Congestion Notification. And it's a very simple idea. Let's say you had a single bit in the packet header, And when your packet hits a congested router, it just sets that bit. And when the receiver receives a data packet that has a congestion bit set, or the ECN bit set, it just reflects that back in the acknowledgement to the sender. Is the basic idea clear? I send a data packet. If there's a router that's congested, it sets a bit. The sender learns about that bit. One bit of information, just a router saying I'm congested. And so there's a design space here about exactly when should the router send the bit. Is it when your average queue utilization is over 75%, or your standard deviation is something or the other? We're not going to worry about that. Let every router decide when it thinks it's congested, set a bit. And there's also a whole design space of how hosts should react when they get that congestion bit set. The easiest way to react is to treat it as loss. It's like an early indication of loss, of congestion. Okay. Advantages of having ECN: you don't confuse corruption with congestion. It's an early indicator of congestion. You can set the bit before you actually fill your queues. So this is another way of avoiding large delays, is to use something like ECN. And unlike fair queuing and unlike RCP, this is a very lightweight mechanism. It's just a router flipping a bit in the packet header. So ECN is widely implemented in routers. It's also quite widely used, particularly in data center congestion control algorithms. Microsoft Azure, for example, uses ECN for its congestion control within the data center. One final crazy idea just to share, so you know it exists, is this notion of congestion-based charging. The idea here is not really, it's not a technical change so much as it's a change in business model. The idea was, what if we used ECN as congestion markers, and then users or senders have to pay more depending on the number of ECN bits that they get back. The idea here is the number of ECN bits you get back is a direct indicator of how much you, as a sender, are congesting the network. And so if you pay in proportion to that, the level of congestion you've caused, then that's actually fair. And it also has a way of naturally regulating demand. So in this, the appealing thing about this, it's an elegant intellectual idea. There's no debate over what a flow is or what fair is. It does require an entirely new kind of business model around how the internet works. But theoretically, you can prove that if you have a notion of network utility as user happiness, in the sense of, as a user, what maximizes your happiness as a combination of the performance you're getting and the amount of money you're paying, then actually congestion pricing is optimal. That if you do congestion pricing, you maximize user happiness or the network utility. Okay? We're not going to go there. So recap, router-assisted congestion control. Fair queuing is routers enforcing per flow fairness. RCP is routers informing end hosts of their fair share. ECN is just routers informing end hosts of whether they're congested or not of the actual fair share. And congestion pricing is the idea that users pay based on congestion. Pulling all of that together, perspective on router-assisted congestion control, as you saw from that RCP graph, highly effective, can actually be optimal in many ways, but the deployment is more challenging. We need to upgrade routers. Some of these mechanisms are heavyweight to actually put in routers, but computational technology and algorithms are improving every day, so maybe the day will come. And some of them actually require deployment at every router, which can be difficult to deploy on the internet. That said, all of these constraints are much less of a concern in data centers, so many of these ideas are actually still under investigation or have been adopted in some cases in data centers. And so finally, wrapping all of this up, perspective on TCP congestion control, it's not perfect, it's a little ad hoc. There are certain rules that you say, why 3, why not 4? Why do you start with an initial window of 10? So there are certain ad hoc choices. It is deeply practical and deployable. The basic idea that drove Van Jacobson's thinking remains and has held. And it's good enough to have raised the bar on deployment for more optimal approaches. So for example, fair queuing on paper might seem like the perfect thing to go deploy. But until you really need it, no one's going to go and put that level of complexity into routers. And finally, when we get to data centers, we'll revisit some of these ideas, because a lot of the constraints around, you can't deploy at all routers, or you can't have all senders do the same thing, go away in data centers where you have one operator kind of controlling the end-to-end picture. Right? With that, any questions? If not, next topic will be the DNS, Murphy's lectures. We'll be releasing those recordings, and remember, no in-person lecture on Thursday. Okay? Thank you.